In the first part of the talk, we started to see some pictures of manifold with codimension 2 singularities, and now we're going to give a precise definition. So we consider a compact metric space. We say that it is a manifold with simple energies of codimension 2 if we can decompose it in two parts, one regular set and a singular set. So the regular set is an open boot and manifold, which is dense in the whole space, while the singular set is an n-2 manifold. We need to explain what is the local geometry close to the singular set, and we want it to be conical. So the idea is that if you pick a point in the singular set, you always find a neighborhood of it, which is homomorphic to a product of a ball in a Rn-2 and a truncated cone over a circle. And here, a truncated cone, I mean that instead of taking the product between R plus and the circle, we just take an interval and the product between an interval and the circle. And now we want to have a metric on this singular manifold, and we assume that there is a Riemannian metric on the regular set, which induces the same metric as the one that I gave before. And we need this metric to have a precise behavior close to the singularities. So this behavior needs to be conical. So we ask it to be close to the model metric GA that we had on Rn-2 cross the cone. So more precisely, we consider the metric GA on Rn-2 cross the two-dimensional cone. So this puts an angle 2PA along Rn-2, and we pull it back to the neighborhood UP. So this difference between the actual metric G on the manifold, the singular manifold, and this pullback of the model metric needs to be controlled by something, the distance from the singular set R, and this needs to go to 0 with R. So when you get closer to the singular set, the metric G gets closer and closer to the model metric GA. This is exactly the translation of this picture that we have seen before. At a point here of the singular curve, you find a tubular neighborhood, which is of the form of an interval across a cone. And you want that the metric, when you get close to the singular set, get close to this model metric that gives an angle 2PA to this singular curve. So in general, if you use this definition, you have a well-defined angle along the codimension 2 singularity, and this angle is given by 2PA, where A is the parameter here in the model metric. If you consider the example of the singular spheres, Sn with the metric Aj, which was the pullback on the sphere of this metric Ga, of a conformal factor of this metric, then you can also write it as a double word product between an interval Sn-2 and a circle of radius A. It is not that difficult to see that when you consider this double word product metric, and it's asymptotic when rho goes to 0 or rho goes to pi over 2, you understand that when rho goes to 0, you don't have any singularity, but when rho goes to pi over 2, you find the good asymptotics and you have a conical singularity of codimension 2 along this Sn-2, okay? So again, this singular set of the singular spheres is a grid circle of codimension 2, and it has angle 2 pi a, okay? Now, some of the results that I'm going to state actually hold in a more general setting, which is the one of stratified spaces. So in order to understand what stratified spaces are, you just need to modify a bit the previous definition that we gave. So the first thing is that the angle 2PA along the codimension 2 singularity can depend on the point. It is not necessarily fixed along the singularity. In our case, it will be, but you can consider something more general. Moreover, stratified spaces are called like that because the singular set sigma has different strata, meaning different components of possibly higher codimension than 2. So the singular set is in general composed by pieces sigma j of dimension between 0 and n minus 2. And when you consider a point at the stratum of dimension j, then a tubular neighbor of it will be of the form of some ball in Rj, and a cone over some metric space Zj. This metric space is also a stratified space, so you can have singularity one into another. In particular, this link, as I said, can be a stratified space. And if you consider the case of orbifolds that are in stratified spaces too, the link here is usually a quotient of the sphere, which is not necessarily smooth. And again, you can define Riemannian metrics on stratified spaces in such a way that there are just Riemannian metric on the regular set, and they have precise asymptotics when you get close to the singularities. And since singularities can be one into another, actually an iterated edge metric is defined by iteration on the dimension and by closeness to some model metric on the product between Rj and a cone over the link. So stratified spaces had been introduced first in the 40s as a way of studying topological spaces with the idea of decomposing a topological space into nicer pieces that are given by manifolds. Later on, or starting from the 80s, they were studied from a spectral point of view. Indeed, Jeff Chigger published a paper about spectral analysis on manifold with conical singularities. And starting from that, there's been a lot of work on understanding analysis and spectral analysis on manifold with simple edges, and later on stratified spaces. And the tool that is most used is the microlocal analysis that we're not going to use in this talk. And recently there has been some work about the Yamabe flow on manifold with simple edges. Studying the Yamabe flow can give another way of solving the Yamabe problem if you're able to get long time existence and convergence. And this is done by Boris Wertmann, Erik Bauwoud, and student of Boris Wertmann. Okay, so we want to study the Yamabe problem on this manifold with singularities, when it is the easy case, just singularities of codimension 2, and sometimes also with higher codimension singularities. And in order to do that, and to give the definition of the Yamabe functional, the Yamabe constant, we need to fix the notation for what the Sobolev space is. So the Sobolev space is simply the closure of the set of Lipschitz function on the compact stratified space with the usual norm of W12. And Kazuo Akutagawa, Gilles Caron, and Raif Mazzeo proved that the Sobolev space on a compact stratified space as the usual embeddings that you have on a compact smooth manifold with compactness when P is not critical, meaning when P is different from 2n over n minus 2. And this is useful in order to get a good definition for the Yamabe functional. So remember that the Yamabe functional on a smooth manifold was this quotient where U is a conformal factor of the metric. So here, this functional is also well defined if you assume that the scalar curvature of the space belongs to LQ for Q bigger than the dimension over 2. And if you pick a function U in the Sobolev space, and thanks to the embedding, you have something, and this assumption on scalar curvature, you have something that is well defined and bounded from below. And since it is bounded from below, you can define its infimum, and this gives you the Yamabe constant of the whole stratified space. So the idea is, again, you try to find a metric, G tilde conformal metric, for which the conformal factor minimizes this Yamabe functional. So it is such that the Yamabe function computed on U is exactly equal to the Yamabe constant. Once you have that, even if the function is in W12, you can apply regularity and you will find that the conformal factor is actually smooth on the regular set. And if you find a metric like this, then this will have constant scalar curvature on the regular set. So this is what I mean for a Yamabe metric is in this setting. It is a minimizing metric for the Yamabe functional, which has constant scalar curvature away from the singularities. So here, remember that in the case of compact smooth manifold, in order to find existence, you need to study the Yamabe constant, this conformal invariant. And one key point was the Aubin inequality. It showed that the Yamabe constant was less or equal than the Yamabe constant of the sphere. And if the inequality is strict, then you have existence. So that was one of the first steps in solving the Yamabe problem on compact smooth manifold. Here, if you ask the Yamabe constant of the global, of the stratified space to be strictly less than the Yamabe constant of the sphere, this does not give any information about existence. And we will see why. You need to introduce a new conformal invariant, which is the local Yamabe constant. Remember that the Yamabe constant of the sphere was in some sense the limit of Yamabe constant of small balls when the radius goes to 0. So let's start by defining the Yamabe constant of a ball in a stratified space. And this is the infimum of the Yamabe functional, as before, of functions that are Sobolev and compactly supported in the regular part of the ball. Okay, so now consider the limit as the radius goes to 0 of the Yamabe constant of the ball. If you pick a point P in the regular set, then it is a point belonging to a smooth manifold, and the limit here will just be the Yamabe constant of the sphere. But you also have singular points. So you need to take the infimum over all points in the stratified space, and then the limit as r goes to 0 of the Yamabe constant of a ball. And this is, of course, less or equal than the Yamabe constant of the sphere, and in particular, it can be strictly less than the Yamabe constant of the sphere. So this is the conformal invariant that you need to study in order to get some existence or non-existence. And of course, we have a generalized Aubin's inequality because this limit will always be bigger than the global Yamabe constant because you're taking the infimum over a smaller set of functions. So in the case of just codimension two singularities, the local Yamabe constant will actually be the Yamabe constant of the codimension two singularities, meaning the product between Rn minus 2 and the two-dimensional cone with the metric GA that puts a conical singularity of codimension 2 in Rn. So here you have an open space, it is not compact, and it is singular. So it is not very easy to compute what is this Yamabe constant. It is in general not very easy to compute Yamabe constant. So in 2014, the paper was accepted later, I proved the following. If you consider a manifold with simple edges of codimension 2 and of angle 2 pi a, you have two possibilities. Either the angle is less than 2 pi, so the parameter is less than 1, and the local Yamabe constant is strictly less than Yamabe constant of the sphere by a factor a to the power 2 over n. Since a is less than 1, this is strictly less than the Yamabe constant of the sphere. Or if a is larger or equal than 1, then the local Yamabe constant is exactly equal to the Yamabe constant of the sphere. So in some sense, in this case of angle bigger than 2 pi, you don't see the singularities in the local Yamabe constant. So the first one is the more difficult to prove, and it relies on finding the good Sobolev inequality with explicit constants. That depends only on the volume and on dimension of the stratified space. And this is done by using a spectral gap on the compact stratified space in the form of Alice-Norowitz theorem. The second one is a bit easier, and the idea is that you prove a Euclidean isoperimetric inequality on the space Rn minus 2 across the cone when A is bigger than 1. And when you have a Euclidean isoperimetric inequality, you also have the same Euclidean Sobolev inequality that you have on Rn, and this Sobolev inequality is as an optimal constant that gives you the Yamabe constant of the sphere. Okay, what are the consequences of this result in the case that we are going to consider most, which is the one of singular spheres? So remember, singular spheres were spheres with this pullback metric that puts an angle an angle 2 pi a along a grid circle of codimension 2. So the stereographic projection here is a conformal diffeomorphism. So the singular spheres are actually conformally equivalent to the product Rn minus 2 across the two-dimensional cone. And since the Yamabe constant is a conformal invariant, the Yamabe constant of singular sphere is exactly equal to the Yamabe constant of the corresponding singular Rn. But now the singular spheres are manifold with simple edges of codimension 2. And the previous results tells you that the local Yamabe constant is exactly equal to the Yamabe constant of this singular Rn. So here we are in the case of equality between the Yamabe constant of the singular sphere and the local Yamabe constant of the same space. And now, if A is less than 1, you have this value for the Yamabe constant of the singular sphere, and if A is bigger than 1, then you just get the Yamabe constant for the smooth sphere. Now, it is not difficult, it's just a very easy exercise to compute the Yamabe functional on Aj, okay? The scalar curvature of Aj is always n times n minus 1 on the regular set of the singular sphere, and then you can compute the volume, and you get that the Yamabe functional over Aj is just a to the power 2n times the Yamabe constant of the smooth sphere. So when A is less than 1, Ha attains the Yamabe constant of the singular sphere. These two quantities are exactly equal, so Ha is a Yamabe metric. And this is actually a particular case of a global fact, which is the following. If you consider a manifold with codimension 2 singularities of angle less than 2 pi, and you have an Einstein metric, then this Einstein metric is a Yamabe metric. This is not the case when the angle is bigger than 1. Indeed, here you have an example. When you compute Q, the Yamabe functional of Aj, you get, since A here is bigger than 1, you find something which is strictly bigger than the Yamabe constant of the sphere. So you find something which is bigger than the Yamabe constant of the singular sphere. So Ha is Einstein, but it is not a Yamabe metric. And this gives us the guess that when A is bigger than 1, there are no Yamabe metric. Even if this is Einstein, it is not Yamabe, so there might not be any Yamabe metric. Now, our proof of the non-existence when A is bigger than 2 is by contradiction. So we will assume that a Yamabe metric and thus a Yamabe minimizer does exist. So we will need to use properties of the conformal factor of a Yamabe metric, so the Yamabe minimizer, in order to get to a contradiction. So in the following part, I will explain some of the results that are known about Yamabe minimizers. So first of all, an existence result due to Kazuo Akutagawa, Gilles Caron, and Raif Matseo. If you consider a stratified space of dimension larger than 3, so note these are generally stratified spaces with possibly higher codimension strata. You assume that the scalar curvature is in LQ for Q bigger than dimension over 2, and a strict generalized Aubin inequality. So you assume that the Yamabe constant of the whole space is strictly less than its local Yamabe constant. Then under those assumptions, you always find a Yamabe metric and a Yamabe minimizer that belongs to W12 and is bounded on the whole space. Moreover, something that we are going to use later, the Yamabe minimizer satisfies an equation, the Yamabe equation, only on the regular set. So you know something about the Laplacian of Yamabe minimizer, and this is important. So note that here, if you consider Viaclovsky's example, which is an example of a compact stratified space, in this case, the global Yamabe constant was exactly equal to the local one. And this is also the case for the spheres, the singular spheres with angles larger than 2 pi. Now, when a Yamabe minimizer exists, you can get more information on its regularity if you assume that the metric is Einstein on the regular set. So note here that we are assuming that the metric is Einstein on the regular set, but we are not assuming that we have only codimension 2 singularities. So this regularity result is true even if you have other strata of higher codimension. And everything depends only on the angle of the codimension 2 singularity. So if the angle is less than 2 pi, then a Yamabe minimizer is actually a Lipschitz function, and you have a very good control of the norm of its gradient, which is bounded and Sobolev. While when A is larger than 1, you have something which is less good. The Yamabe minimizer is just older continuous with this exponent nu here that is 1 over A, so it depends on the angle. And you can also deduce a behavior for the gradient of the Yamabe minimizer, which is given by the following. When you look at the L infinity norm away from a tubular neighborhood of the singular set, then you control this norm by the size of the tubular neighborhood to power nu minus 1. Notice that here nu is less than 1. So when epsilon goes to 0, this quantity explodes. So the gradient potentially goes to infinity when you approach the singular set. So this first part was proven in a paper of mine on 2018, sorry. And the second part is in the paper, joint paper with Kazuo Akutagawa. And the ingredients for this proof are a regularity result due to Kazuo Akutagawa, Gilles Caron, and Matteo. Again, a lower spectral bound in the style of Lichtenowitz theorem that they proved, and Moser's iteration, Buckner formula. So it's an analytic result. Okay, so we have all the results that we are going to need in order to give the proof of the main result with Kazuo. So this will be in the last part of the talk.